My life be like, yeah. My life be like, yeah. Yeah. My life be like, yeah. My life be like times like these that make me say, yeah. Lord, if you see me, please come my way. Like leaving breadcrumbs so when I stray. Yeah, a lot of sacrifice in the price you pay. Like living like a fingertip. Sometimes I fall, I slip. Yeah, more feelings I be more like you. Yeah, not to put you fire with the things I like. I'm on an island by my lonesome stranded. Low key and staying candid. Reflect on all the things I try my hand at. Search for the equation to persuasions I'm used to. Find a comfort in the zones of clouds and bones I get loose to. A mountain is Fontaine. Spinning in monsoon and grinning this high octane. Explosive how I came. Rolling down the hills cause life's a hassle.
Hello, everybody. These are your video notes on related rates. So my goal is to introduce related rates and then do 2 examples with you so that when you come back in class, you can start working on different practice problems that have to do with related rates. So we did the intro in class on related rates and talking about how in different scenarios, the rates are not always constant. Before you can do a related rates problem, though, I have to make sure that you can correctly take the derivative with respect to time, and that is called ddt. So remember, ddt is like a command. It's saying, hey, take the derivative with respect to time. So like I said in class, typically you'll be doing geometry inspired situations. So you'll have to know your geometry formulas. I'm going to do a couple of these. Then I would like you to finish this half sheet of derivatives. You can choose to do it now, like pause the video and then do it, or you can finish it after the video. It's totally up to you. So let's start with the basic one, just so you can get the idea of it. So this is obviously the area of a circle. Derivative rules that applies. That mainly means like you have to do the basic power rule. Do you need product rule? Do you need quotient rule? This one here, I have pi times r squared, but you don't need to use the product rule because it's a constant, which is pi times a function, r squared. So I'm just going to say power rule. You can call it the basic rule. They're kind of the same thing. So I'm going to do the derivative with respect to time. So any variable that is not a t needs to have d something dt after it. So if I do the derivative of this, and remember, you're doing the derivative of both sides. So I'm going to do the derivative of a with respect to time, which is technically 1, but then I need dA dt after, kind of like the chain rule. All right, pi is a constant. It goes along for the ride, times the derivative of r with respect to t is 2r, but then I multiply by dr dt because r is not t. You can rewrite this so it looks familiar, 2 pi r dr dt. So in calculus, the derivative of an area is a distance, because this is actually the circumference formula, 2 pi r. Kind of like the derivative of position is velocity, and then derivative of velocity is acceleration. There's connections between the geometry formulas as well. I would like to do this one with you as well, just so you can see a product rule, and I'll make sure that you're going to be okay. So this is volume of a cylinder. Volume of a cylinder. Okay, so this one is going to need product rule because I have that pi there, but then I have r squared times h, and r squared and h are 2 different variables, so you can't avoid product rule here. So I'm going to do the derivative with respect to time, d dt. So derivative of v with respect to time is dv dt. I'm going to keep this pi on the outside. Like you could choose to rope the pi up into the r squared term and like keep them together for product rule, but I'm going to keep it up front. We'll end up with the same thing no matter how you do it. So I'm going to do pi. Then I'm going to do my product rule. So I'm going to keep r squared the same times derivative of h is technically 1, but then dh dt plus, and then, okay, derivative of r squared would be 2r with dr dt, and then h stays the same. If you kept the pi with everything, it'd be pi r squared dh dt plus 2 pi r h dr dt. That is from distributing the pi to each of these 2 terms and just kind of rearranging. So I would like you to finish doing the derivatives of these. Some of them are super basic, and some of them need product rule. So like this one right here, when you do this, again, you need product rule. And this one right here, make sure, actually, no, wow, that one is not product rule because 4/3 and pi are constants. So go ahead and try these. Like this one here, you're going to need product rule with the b and the h, and then L and W. All right, so go try those. Remember, it's derive with respect to time. Let's go ahead and try a problem. So right now in your notebook, you have this thing taped down, and then I'd also like you to tape down this. This was a little slip I gave you so that you don't have to write the steps down, and make sure you tape it now so that you have it to look at. Now this should not say T on it. All right, so these are the steps we're gonna go through. There's 9 main steps. And as we do this problem out, I'm gonna write out the steps, like I'll number them so that you can follow along as we do the problem. The first problem that we're going to do is related to a circle. So we're going to have a spherical balloon, so another balloon scenario. And we're going to assume that it's going to stay in the shape of a sphere the whole time. And the volume is, the info that we're given is the volume is increasing at a rate of 100 cubic centimeters per second. How fast is radius increasing when the diameter is 50 centimeters? Okay, so the first thing you're going to want to do whenever you do these problems is get a visual and label it with your variable. So that's going to really help figure out how to fill out your table of given information. So I have a balloon here. The volume is like this overall thing here. And basically the only thing we can label is radius. I'm not going to use diameter in this problem because I want to know how fast the radius is increasing. So I'm just going to turn this into a radius of 25. And that will allow us to use a formula. So they tell us that the volume is increasing at a rate of 100 cubic centimeters. Anytime you see something cubic, that has to do with volume. So sometimes people see information and they're not really sure what variable to put it with. Cubic goes with volume. And it's cubic centimeters per second. That immediately means it's a rate, and it's the rate of change of volume. So I call that dV dt. 100 centimeters cubed per second. So let's talk about the table setup. I'm always going to ask that you do a 2-column table, and on the left is going to be the variable information, and on the right is the derivative or the rate of change information. I have d blank dt because like it's dv dt or dr dt depending on the variable. Next to each rate, you should put the corresponding variable that goes with it so that you stay organized. So my first row is volume information. Now, they don't tell me what the volume is when the diameter is 50 seconds, but you can find it. That's like subtle information. It's very important to know the difference between subtle information and the big unknown. The big unknown is what you're solving for. That's going to get a question mark. All right, they tell us the diameter. I'm just going to go ahead and put radius because that's going to be in our problem. And dr dt. So every variable should have a rate that goes with it. Dr dt. Do I know dr dt? Well, okay, how fast is the radius increasing? That's what I'm trying to find. Every table needs a question mark. It's very important that you put a question mark in the table. Sometimes I find that people avoid putting a question mark in the table because they don't really know what they're solving for, and then they just kind of go in circles. So don't do that. There's one question mark. That's what you're looking for, and that's going to guide your entire solution process. Okay, let's go ahead and find V here. So what formula can I use to find V? Volume of a sphere. Well, that's 4/3 pi r cubed. So write this down with me here so that you can keep up with what's happening. 4/3 pi. Now I know the radius. It's 25 cubed. So that would be 4/3 pi. 25 times 25 times 25 is 15,625. And I'm going to 20833 point. I multiplied that out. And I'm going to keep it in terms of pi. You could definitely multiply that number by pi and get another decimal. And you're going to find that we actually don't really need this number, but it's still good to fill out the table just so it's complete. Okay, my table is filled out. Again, subtle information is information you can find pretty quickly, but it's not the big question mark. It's just the subtle information just lets you get a complete table. So my table is complete. Every row and box is filled out. I know what I'm looking for. Step 5, the signs. So this balloon is increasing, so the rates should be positive. That you just have to be careful of, like, are any of my rates negative, for example? Definitely not here. Okay, let's go ahead and do step number 6, which is you need a formula that relates the variables in the problem. And we kind of already found it because I have volume of a sphere and I have radius of a sphere. So what formula is going to connect those together? And that is the volume of a sphere formula. When you write this formula out, you should double check, the variables in here, are they the same as the variables in your table? If they're not, then that formula is not going to work. It's very, very important. If you pick the wrong formula and then do the derivative of it, you're not going to be able to substitute into it. Okay, let's go ahead and do step 7. So this is a related rate problem. I'm dealing with rates. So I need a derivative because you can't do rates without a derivative. So this is why you needed to do the half sheet to do that half sheet, the table, because we're going to do derivatives with respect to time. So the derivative of volume equals 4/3 pi r cubed with respect to time is dv dt. Now this constant, 4/3 and pi are both, well, they're coefficients. Coefficients go along for the ride. This is my variable term. The derivative of r cubed is 3r squared times derivative of radius with respect to time. I would always recommend you simplify right away. Sometimes I see people and like they don't cancel things whenever they can cancel it, and then they're dragging along all these constants and coefficients that you don't need to be dragging along. So simplify as you go. Your numbers will be more manageable. It'll be easier to substitute, etc. So this is a simplified derivative. Another important thing, don't substitute until you have a simplified derivative. You always do a derivative first and then you substitute your values in. Okay? So step 8, let's go ahead and substitute. Okay, I need to be plugging in dv dt. 4 and pi are constants. I know my radius. This is the big question mark. All right, so I'm going to have 100. That was the rate of change of volume. 4 pi r is 25 squared, and dr dt. Last thing we have to do is just solve for dr dt. The hard part is done. This is really just algebra at this point and simplifying. So if I want to solve for dr dt, let's move all of this to the other side. So divide by 4 pi 25 squared, 4 pi 25 squared. And let's talk about how we can simplify this, because sometimes this will be a multiple choice where it'll be calculator active and then you get a decimal. And sometimes these will be no calculator and you need to be able to simplify a little bit. So like what if I took 4 times 100, 4 times 25, which is 100. That will cancel with this 100, which would leave a 1 on top and a 25 pi on the bottom. So you want to be able to like cancel constants like that in case it's a no calculator problem. Now, another really important thing is units. You don't want to do this without units. So what on earth is the unit of the radius changing with respect to time? If radius is centimeters, then dr dt will be centimeters per, and what's time here? Second. So you need a rate unit. So the change of radius with respect to time. Okay, so my radius is changing at that. And if you want a decimal, like if it's easier to think about what this number is, so 3 decimal places would be this. So very slowly, 0.013 seconds per centimeter. That's how quickly this radius is changing. Every centimeter is changing at 0.0127 centimeters at this moment in time when the diameter is 50 centimeters. So they didn't give us an actual time here, but the way you stop this is whenever diameter is 50 centimeters. So speaking of time, let's do a problem where you are given time information, because these types of problems have a slightly different process, just a little bit. You have to think about time here. Okay, so we're going to do the same process here, and let me get the steps like outlined here. Hold on. Okay, second problem. Stay with me here. This is a cool one, and we're going to talk about time. So here we have a railroad track and a road are crossing at 90 degrees. So like this, 90-degree angle. We have a person standing 70 meters south of the crossing. They're watching an eastbound train traveling 60 meters per second. So this train is flying past this intersection, 60 meters per second. So how many meters per second is the train moving away from the person 4 seconds after it passes through the intersection? So 4 seconds after this moment. We let it run for 4 seconds. Then we stop time, and we want to calculate the rates at that exact moment. All right, so what are we even looking for here? How many meters per second is the train moving away from the person? So here's the person. After 4 seconds, the train would be somewhere around here. This rate right here. And we have a triangle in this scenario. So that is the hypotenuse. Okay, let's get an actual triangle because that's going to help us fill out a table. And I want to label my triangle for after 4 seconds have passed. I don't want it at this moment in time when the train is right here because like I don't even have a shape right there. That's just a vertical line. So 4 seconds later, the train is somewhere over here. So this is where the train is. This is where the person is. And let's simplify this diagram and label it. Now, since we have a triangle, I always recommend you do X, Y, and Z. You can do A, B, and C, but don't I would definitely recommend with one of those setups because sometimes people pick weird variables and it's hard to follow the process. Also, don't make this be X and this be Y. I always have people who like label it like that and then they mix up the rates because, it makes sense that the vertical one is Y. So fill it out so that it logically makes sense with your labels. So I'm going to let this be Y and this be X, which means this is Z. And let's see, like, what do I already know? Okay, I have X, Y, and Z. And for every variable, you should have a rate that goes with it. It's either going to be given or it's subtle or it's the big question mark. And you have one question mark per table. Okay, my person is 70 meters south of the intersection. So that is 70. Do I know dy dt? Now think about this carefully. If the train is moving this way and this person is never moving, this distance never changes. So if the distance y equals 70 never changes, that means dy dt is 0. That's going to happen in kind of a lot in different problems, depending, especially in triangle problems. All right, what about, so I did 70. I'm going to check off every number, make sure I got it. I'm traveling 60 meters per second. Okay, that's a rate. And it has to do with a train. So the train's rate, so I can put a dxdt here, is 60. So 60 meters per second. How many meters per second is the train moving away? All right, that's here. So I'm looking for dz dt. That's my big question mark. Okay, 4 seconds after it passes through. Now, I'm not going to put time in my table. Time is going to help me fill out my table and get me my subtle information. So all I know is that y is 70. This is subtle, and this is actually subtle as well. So let's think about like how can I get x and z? If the train is moving 60 meters per second and I let it run for 4 seconds, I can find out my x here. Initially, x is 0, and then if I'm moving at 60 meters per second for 4 seconds, seconds cancels, leaving me with meters. So 60 times 4 is 240 meters. So that is actually your x value, 240. Sorry, ignore that right there. 240. That's my first subtle piece of information. So after 4 seconds, x is 240 meters. I stop time at that moment and I calculate dz dt. So dz dt is a question mark. Okay, all I need is z and then we're in business. This looks like Pythagorean theorem. So x squared plus y squared equals z squared. My x is 240. So 240 squared plus my y is 70 squared equals z squared. So what this ends up being is 62,500. And you could obviously get that if you actually squared those and added them together. But what the heck am I doing? Okay. And then to find z, what you're going to do is the square root of each side. That's where the square root comes in. And this ends up being an exact answer of 25 for z. So I'm going to put 25 right there. And I'm going to put 25 right there. So take a second and make sure you're all set with what's happening. Okay, I just checked that number 62,500 because I wanted to make sure that was all set. All right, z is 25. So now what we need to do, this is the hard part is done. Once you have filled that out, now it's just do a quick derivative and plug in. Are any rates negative? So this is not changing. X is increasing, so the rate's positive. And this distance will be increasing, so that rate is going to be positive. dy dt is 0. Step 5 was checking the signs. Let's do step 6. What formula relates these variables in a triangle? And that would be Pythagorean theorem. So x squared plus y squared equals z squared. A lot of times the formula you use for the subtle information is also the formula that you're going to end up doing the derivative of and differentiating. So my next step for 7 is to actually do a derivative. Do not plug anything from the table into here. Like, don't start actually solving for dz dt until you've done a derivative. ddx or 2x dx dt plus 2y with a dy dt equals 2z dz dt. So basically every variable needs d something dt after it. And the one that I'm looking for is this. Now, one thing that I personally like to do, which you definitely don't have to do, but that I often do, is I cancel the 2's at this point. Just so, again, that my numbers are smaller. And especially if it was a no calculator problem, I want small numbers. So if you want to rewrite it cleaner, you can, or I mean, you could have plugged in at this point. So step 8 is to substitute. So let's go ahead and substitute our values in. So this is just simpler and cleaner. My numbers will be smaller. X is 240, dx dt is 60, plus y is 70, dy dt is 0. Love whenever there's a 0 because that just zeroes out. And dz dt. Okay, so this is gone. I have 240 times 60. What is that? 14,400. So 14,400 equals 250. And last thing, just divide by 250. And you get 57.6. So that's dz dt. That is a rate of change. Now I'm just checking the units here. That would be meters per second, right? Yes, meters per second. So that means at exactly that one moment in time, this rate is 57.6 meters per second. And that rate will change. Like if the train was here, that rate would be larger. And as the train moves further and further east, that rate will decrease because like you have to turn your head less and less to keep the train in your line of sight. All right, that is all. So make sure you wrote this down carefully. Make sure you have all the information, your table, your diagram, your work shown, and get excited to do these in class together. Bye.